let's talk about verifying trigonometric identities. So to verify a trigonometric identity means to make the two sides of a given equation identical to each other in order to prove that it is true. Now, there are a couple of different rules and thought processes that we have to keep in mind as we are applying and verifying trig identities. And I've really wanted to emphasize the following point. When we are verifying trigonometric identities, we are only allowed to work on one side, or I should probably better state that we want to specifically work with one side. So that means we don't want to apply any algebraic operations that involve doing things to both sides or manipulating the equation in that way. Because if you work on both sides, what you're doing is you're showing that if the starting equation is true, then you can arrive at another true equation, right? So if we go back to our first example here, if I were to start doing work to both sides in this first example, what I'm doing is I'm saying, assuming or if the first equation was true, then I can come up with another equivalent equation. But that's not actually proving that the original equation was actually logically true. So when we are verifying trig identities, we want to make sure that we're working exclusively on one side. There's some things that I will allow in this class just to make our lives a little bit easier, and so there's a little less writing, but we'll get to that. The next thing I do want to highlight here is that verifying trig identities can be a tricky process for a lot of students. And so I'm providing a couple of different guidelines here. These aren't really hard, fast, or steadfast rules. These are just some things to help guide you. I do recommend starting with the more complicated side. I always tell students it's easier to take something that is complicated and quote unquote messy looking and make it simpler because we're very used to simplifying than it is to do the opposite, to take something that already looks simple and try to find ways to make it more complicated. When you find yourself that you're stuck, you can always just try to find ways to factor or square or add fractions or to use any applicable identities. And sometimes you may want to just try to rewrite trig functions in terms of the other. So rewrite tangent, for example, in terms of sine or cosine, if you notice that there is a sine or cosine in there. And the last thing, and I know this sounds kind of silly, but just try something. At the end of the day, just try anything. Oftentimes you'll find that just even accidentally by kind of throwing something at the wall and not literally, but throwing something at the wall and trying to figure out some type of trigonometric substitution, it actually leads to a breakthrough and things start to just kind of snowball from there. So there isn't really too much in terms of instruction. It really just comes down to practice and having a firm understanding of our trigonometric identities that we already know. So I hope to just go through a number of these with you all today. So let's get started. So let's start with this first one here. We're going to verify that this is indeed true. So again, we're going to try to work exclusively on one side. As I suggest, I recommend trying to work with the more complicated side. Now, I should also point out that there is more than one way to go about doing this. There are actually a number of different options here. Some of you are probably looking at this and already are thinking about maybe substituting secant squared theta minus 1 for a tangent squared theta using the Pythagorean identity. But one thing that I'm going to do here, just this is my first instinct, is to actually rewrite this as two separate fractions. So I'm working with the left side. I'm going to write the following. Secant squared theta over secant squared theta minus 1 over secant squared theta. Okay. And what that does is it allows me to rewrite this as the following. 1 here minus, and using the reciprocal identity, 1 over secant squared theta is just simply cosine squared theta. And that is equal to sine squared theta. And 1 minus cosine squared theta using the Pythagorean identity and that substitution, we can just write that as sine squared theta. So I've shown that this equation is logically true. We've proven that the original equation was actually true by actually just stating every single step of the way what this is equivalent to. That we've simplified it down to sine squared theta. We are showing that it is equal to what we were initially setting to prove from the get-go. I like to just do this little check mark that just indicates to the reader that I'm done. Note that every single step that I'm doing this, I need to make sure that I have an equal sign, that I'm writing an equation every single time. It's just bad math to start doing work and not showing equivalent statements, so that will be required, okay? Now again, that's not the only way to have done this problem. If you wanted to make this numerator equal to tangent squared theta and start simplifying from there and using reciprocal identities and quotient identities, that could definitely work as well. I think it might take a few more steps, but it could definitely get you down the path. Let's try this next one. So for me, when I see that numerator, the first thing that jumps out to me is to use the Pythagorean identity to rewrite that as 1. So I'm going to go ahead and write that as 1 over, and I can go ahead and write the following in the same step. So I can do something algebraically to the numerator and algebraically to the denominator, and it would be completely fine. What I don't want to do is rewrite cosine squared theta, secant squared theta, simplify it twice, all in the same step. But I can write it as such here. Now, this actually, once I've rewritten it this way, proves to be a pretty easy verifying problem, because we can see that these will divide out, and we're left with just 1 over 1 is equal to 1, which we can also just write as 1 is equal to 1. Check mark, we're done. All right, let's keep going. Let's try something like number 3. Okay, so oftentimes when we see two fractions, one thing that we often want to do is to find a way to combine them before using identities, which again, you don't have to. I could go ahead and see if there are other identities I can apply before I add, but here it does look like I should probably multiply the top and bottom of each fraction by its conjugate so that I can have the same denominator. So in the first fraction, I'm going to write that as 1 times 1 plus sine theta, which is the conjugate of my denominator. So I'm going to kind of write everything out here, although you probably could have just jumped right to the difference of squares. And do the same thing over here, 1 minus sine theta all over 1 plus sine theta times 1 minus sine theta. And give myself some space to work with. And again, we're going to try to show that this is all equal to 2 secant squared theta. So let's clean this up a little bit. The numerator is just going to be 1 plus sine theta plus 1 minus sine theta. All of this over 1 minus sine squared theta. Now in the numerator, I can see that the 1 and 1s will add to become 2. Sine theta minus sine theta, well, those are just going to negate one another. So we're left on the left side with 1 minus sine squared theta, which, applying our Pythagorean identity, we can rewrite as cosine squared theta. And then using our reciprocal identity, we can just say 2 secant squared theta is equal to 2 secant squared theta. And we are all done. Okay. All right. Let's try numbers 4 and 5. And I'm giving you a guiding principle there for numbers 4 and 5 by saying, don't be too quick to multiply. I know that's our instinct to try to simplify, but sometimes we might want to apply identities first. And it won't always be obvious to us, but that's something we can try doing. So for number 4, for example, let's start on that one. If we go tangent squared x plus 1 times cosine squared x minus 1, let's see what identities we can apply first. Well, we know that secant squared x is equal to tangent squared x plus 1. So all of this is equal to secant squared x. There's a Pythagorean identity for us. And cosine squared x minus 1, well, this is equal to negative sine squared x. And all of that is equal to negative tangent squared x. And that's what we're trying to show that this left side is equal to. Now from here, this is where the wheels should be turning a little bit. We know that secant squared x is 1 over cosine squared x. And this is negative sine squared x. Which means we can write this as negative sine squared x over cosine squared x. And then using the quotient identity, we can just simplify this as such. All right, let's go ahead and try that right side now and try number 5 here. We've got secant squared x minus sine squared x minus 1, and we're trying to show that's equal to negative sine squared x. Again, I'm going to try to apply some identities first. It's a pretty similar looking problem. We've got this being equal to tangent squared x, this being here equal to negative cosine squared x, and you can see that's pretty much the same problem, just using a different set of quotient identities. So this is going to be sine squared x over cosine squared x. And then that would be equal to negative sine squared x. Divide this out with this, and you're left with just the following there. And we're all done. All right. Okay, so I would encourage you to try some of these other problems here on the back page, where we will practice converting sine and cosine and just work through a few of these. And you can check Google Classroom to see my completed notes for these and check your solutions. And remember, there's more than one way to go about doing these. So even if your solutions don't look exactly the same as mine, you're still, as long as you're able to verify and you're following the rules of working exclusively on one side, then you should be okay.